Every great structure, whether we're talking about a massive skyscraper or a life-saving new drug, it all starts with the right building blocks. And in the world of chemistry, one of the most versatile and powerful of those blocks is the alkyne. So today, we're going to give you the builder's guide. It kind of sounds like the start of a riddle, right? What could a super high-intensity flame that literally cuts through steel and the starting point for complex medicines possibly have in common? Well, the answer is this surprisingly simple but incredibly powerful molecule called an alkyne. So let's take a look at the blueprint for this amazing structure. All right, so first things first, what's actually in this blueprint? Let's break down the core structure that gives an alkene all of its unique, building potential. Okay, that is the official textbook definition, and yeah, it's a bit of a mouthful. But let's just cut through all that jargon for a second. The only thing you really need to focus on is right there in the middle, that carbon-carbon triple covalent bond. This C triple bond C, it isn't just a detail, it's the absolute engine of the molecule. It's the source of all its power. See, that triple bond is just packed with potential energy. It makes the molecule unsaturated, which is really just a chemist's way of saying it's reactive. It's ready and willing to form new bonds. That bond also acts like a steel rod, locking the molecule into a perfectly straight 180-degree line. And this whole structure follows a pretty simple formula, CnH2n-2, with the most basic example of all being ethine, which has just 2 little carbons. Now, if you're going to build something, you absolutely need to be able to identify your parts. It makes sense, right? In chemistry, that means we need a universal naming system, so a scientist in Tokyo and a scientist in Toronto can be sure they're talking about the exact same molecule. And the great thing about this is it's not some secret code, it's really just a logical system. It's a simple 4-step process. First, you find your main structure. That's the longest carbon chain that has the triple bond in it. Second, you number that chain, but you do it in a way that gives the triple bond the lowest possible number. Third, you spot all the extra little pieces attached to the chain. We call those substituents. And finally, you just put all the pieces of the name together in order. Simple as that. I know, this name looks super intimidating, but trust me, it's just a set of instructions built from those 4 rules we just talked about. Let's break it down. We actually start from the end. Hexyne tells us we're building with a 6-carbon chain that has a triple bond. The 3 right before it tells us exactly where that triple bond starts, on the 3rd carbon. See? Then we just add the other pieces from the front. A bromo group on carbon 2, 2 chloro groups on carbon 5, and a fluoro group back on carbon 2. It's literally like a blueprint in word form. Okay, now here's where building with molecules gets really interesting. What happens if you take the exact same set of atomic parts, but you connect them in a totally different order? Well, you get molecules that are kind of like identical twins, but with different personalities. We call these isomers. And this is the key idea right here. Imagine you have a box of Legos. You can use all the same pieces to build a car, or you can take it apart and use those exact same pieces to build a house. Same parts, different structure. That's exactly what constitutional isomers are. They have the same molecular formula, but a completely different blueprint for how the atoms are all connected. With alkynes, this tends to happen in 2 main ways. For chain isomers, the actual carbon backbone, the skeleton of the molecule, gets rearranged. It's like changing a straight road into one that has a side street branching off. For positional isomers, the backbone stays the same, but the location of that all-important triple bond just moves to a new spot. So let's look at a real example using the formula C5H. Here, you can see the 5 carbon atoms are all arranged in a simple, continuous chain. We call this particular molecule 1-pentyne. Pretty straightforward. But now look at this. We have the exact same formula, still C5H8, but here, the carbon chain is branched. We've totally rearranged the skeleton of the molecule. This means it has different properties, it has a different name. This one's 3-methyl-1-butene, but it's made of the exact same parts as the last one. It is a perfect example of a chain isomer. All right, so we've got the blueprint, we know how to name the parts, and we even know how to rearrange them into isomers. Now for the fun stuff. It's time to put these alkynes into action and see what they can really do in a chemical reaction. Okay, time to put that builder's knowledge to the test. Here's the question. When you react these compounds with water, which one is going to produce a very specific product called an aldehyde? Now take a second and think back to that core structure we talked about. Which one of these molecules stands out as being the most simple and, well, symmetrical? And the answer is B, ethene. Its perfect symmetry is the absolute key here. Because ethene is so symmetrical, when it reacts with water, it can only form one product, an aldehyde. Any other alkyne that has a triple bond at the end of the chain, like propyne for example, well, it's asymmetrical. And that means it follows a rule that sends the oxygen atom to the more crowded carbon, creating a totally different product called a ketone. It's a fantastic example of how a molecule's structure directly dictates its function. You know, this really gets to the heart of it all. It is just amazing to think that one simple feature, that little carbon-carbon triple bond, is the foundation for a whole universe of molecular construction. So, I want to leave you with this thought. We've only just scratched the surface, really, looking at the basic blueprint. But if the very simplest alkynes can power a welder's torch or create key components for drugs, just imagine for a second what we could build with the more complex structures that we haven't even discovered yet. Keep on building.